Today, we're diving deep into a really fundamental question in AI. Are we actually training our most powerful models in the best possible way? It turns out the two main methods we use are way more connected than most people realize. And a tiny, almost hidden, change in the math that links them, whoa, it could unlock a massive leap in performance.
So let's just kick things off with a pretty bold question. Are we teaching our most powerful AI models the wrong lesson? I mean, we pour billions into compute and data, but what if the very goal we're asking these models to aim for is actually holding them back?
To really get what's going on, we need to look at the two big players in AI training, maximum likelihood and reinforcement learning. Now, they're both incredibly successful, but at their core, they teach models in completely different ways.
So on one side, you've got maximum likelihood, or ML. Its whole goal is to perfectly mimic a data set. It's like giving a student an answer key and telling them, make your answers look exactly like this. The learning signal is super direct. But on the other side, you've got reinforcement learning, or RL. Its goal is to rack up the highest score possible by just trying stuff. It learns from a much fuzzier signal, more like, good job, or nope, try again, which is perfect for when you don't know the exact right answer, like in a really complex video game.
Okay, but here's where it gets really interesting. For some of the hardest problems we're tackling today, think generating complex code or solving tricky math problems, we're using RL. But, and this is the key point from the researchers, it's not because RL is the ideal tool for the job. It's actually a workaround. See, the ideal method, maximum likelihood, needs the math to be differentiable. It needs a smooth ramp to figure out how to improve. But for a lot of these problems, the answer is just right or wrong. It's a cliff, not a ramp. And that breaks the math for the ideal approach. So we've been stuck until now.
So what's the big deal? Well, it all boils down to this really crucial mathematical detail that was basically hiding in plain sight, a hidden approximation right at the very heart of reinforcement learning.
All right, let's get into the math just a little bit because it's actually beautiful. This equation here shows the ideal learning signal you'd get from maximum likelihood. Now, the most important part is that highlighted term, 1 over p theta of x. Think of p as just the model's probability of getting problem x right. So this term acts like a difficulty amplifier. If a problem is super hard and the model only gets it right, say 1% of the time, then 1 over p becomes 100. The math literally forces the model to crank up the learning signal on that problem by 100 times. It's a brilliant, principled way to make the model laser focus on what it's bad at.
Now let's look at the reality, the standard reinforcement learning gradient. See what's missing? That critical difficulty amplifier, it's just gone. In standard RL, every problem basically gets the same weight. It doesn't matter if the model solves it 1% of the time or 99% of the time. The learning signal has the same base strength. And that changes everything about what the model learns to care about.
And this brings us to the core insight of the whole paper. Reinforcement learning isn't optimizing some totally different thing. It's optimizing a simplified version of the ideal goal. It's kind of like trying to listen to a full symphony orchestra, but your sound system is only playing the violins. You're getting some of the picture, for sure, but you're missing out on all the richness and depth of the full performance. So if standard RL is just an approximation, a simplified version, how do we get closer to the real thing? How do we hear the whole orchestra? Well, this is where the researchers introduce a new framework they call MaxRL, and it's designed to elegantly bridge the gap between these two worlds.
MaxRL stands for Maximum Likelihood Reinforcement Learning. And the core idea is just fantastic. It creates a whole family of learning objectives that live in the space between standard RL and true maximum likelihood. The trick is, by adding more compute, specifically by asking the model for more sample solutions to each problem, you get a better and better approximation. It's just like adding more speakers to your sound system. The more you add, the closer you get to hearing that perfect, high-fidelity symphony.
Just like the paper says, MaxRL gives you a principled way to trade compute for quality. And here's the subtle part. With standard RL, more samples just helps reduce the noise in your estimate. But with MaxRL, more samples actually improves the objective itself, pushing it closer and closer to that ideal maximum likelihood target. It's a fundamental shift.
Now you're probably thinking this sounds super complicated, right? That it must involve some crazy new algorithm. But the real beauty of this work is just how simple it is. The math that makes it all possible is surprisingly elegant. Okay, this slide right here basically boils the entire breakthrough down to one tiny change. On the left, you've got the standard RL estimator, reinforce. It averages the learning signal over all n attempts. But look at the max RL estimator on the right. It averages the signal over only the K successful attempts. That's it. That's the whole thing. Just changing what you divide by, all your tries versus just your wins, is the difference between optimizing a simple pass rate and optimizing this much richer, way more powerful approximation of the ideal goal.
And this is just brilliant. It shows how that tiny bit of math translates into the real world. That single highlighted line of code is the only change you need to make. Instead of normalizing across the whole batch of problems, you just normalize the learning signal for each problem by its own number of successes. It's such a simple change in the code, but it's backed by this incredibly profound theoretical insight.
Okay, so the theory is elegant. The code change is simple, but does it actually work? Let's get to the good stuff and see how this thing performs when the rubber hits the road.
And yeah, it really does learn differently. These charts tell a really cool story. The one on the left shows that MaxRL puts most of its learning effort, its gradient, on the hardest problems, the ones with a pass rate near 0. It focuses where it needs to. And the chart on the right shows that because of this, over time, it actually ends up solving a wider variety of problems than the old method.
So the bottom line, this smarter, more focused way of learning translates into absolutely massive efficiency gains. This chart shows performance on tough math problems. MaxRL, the red line, is consistently on top. To get to the same performance level, the other methods would need way more compute when you're testing them. We're talking up to 20 times more. That's not just an improvement, that's a whole new ballgame. And you don't have to take my word for it. Let's hear it straight from the researchers. They conclude that on these difficult reasoning tasks, MaxRL Pareto dominates the current state of the art. Now, that's a fancy academic way of saying it's just plain better. It gets you higher performance with the same or even less compute. You can't argue with that.
So let's just zoom out for a second. A simple tweak to the math, a one-line change to the code, and you get these huge performance boosts. What's the bigger picture here? Why does this one change matter so much?
Well, this research really leaves us with 4 big takeaways. First, how our models learn is just as important as what they're learning from. Second, it suggests that a lot of the limitations we thought were just part of reinforcement learning might actually be problems with the objective we were giving it. Third, and this is the exciting part, a better, more principled objective can unlock just staggering gains in both performance and efficiency. And finally, it's a beautiful proof that with some clever math, we can build bridges between these powerful training methods and get the best of both worlds.
And that leaves us with a pretty fascinating thought to end on. We just saw how changing a single term in an equation can completely transform how an AI learns. It really makes you wonder, doesn't it? If the objective function, the very definition of success we give our AI, is this powerful, what other massive breakthroughs are just sitting out there, maybe just one elegant equation away?